Hello everyone, welcome to part 2 of lecture 8. And in this lecture, we will discover some example, we will solve some example to make your concrete your understanding of exponential distribution. Let's look at the first example. The exponential random variable give good models for the time to failure of mechanical devices, okay? So, but that doesn't mean necessarily the exponential distribution is used only for the mechanical devices, but that sometimes gives good models for that kind of problem. So, for example, we might measure the number of kilometers traveled by a given car before its transmission ceases to function. So that's mean at some point the transmission will stop to work properly, and we can solve when that transmission will be failed at some kilometers. So from this context, suppose that this distribution is governed by the exponential distribution with the mean 100,000 kilometers. And what is the probability that the car's transmission will fail during its first 50,000 kilometers of operation? So actually, what I'm asking is remember the CDF of the exponential distribution, which is something like that, right? Which is something like that. And this is the CDF. So there is a point something here that corresponds to 50,000 kilometers. And I just need to calculate the area of this region, right? So that will give me the probability of the Px will be less than or equal to 50,000 kilometers. So this is actually what I am asked, okay? So let x denote the kilometers when transmission fails. It's a random variable. It is given that x is exponentially distributed with the rate lambda is equal to 1 over 100,000. How we get these values? Remember that the expected value of the exponential distribution is 1 over lambda, and that mean actually the mean of the distribution. So that is given, which is 100,000 equal to 1 over lambda. So the lambda will be 1 over 100,000. And remember that the CDF of the exponential distribution was fx, which is equal to 1 minus e to the minus lambda x. Okay? So if I put the lambda values into this formulation, that will be 1 minus e to the minus the lambda is 1 over 100,000 times x, which is 50,000. So if you do that simple calculation by your calculator, you will get approximately the 0.39 something. So which is the probability of that transmission will fail before the 50,000 kilometers, okay? In other words, that value is the area of that region. Let's continue with the second example. In this example, let x be an exponential random variable with rate lambda, and given that the x is greater than t1, we know that information is given to us. What is the conditional probability that x greater than t1 plus t2 for positive t1 and t2? Let me draw something to make it clearer. In that is the t1, and that, let's say this is the t2, and let's say this is the time interval, okay, from 0 to infinite something. From 0 to t1, that is the first part, which is t1, and let me clear that part, that one. And from this point to this point, that will be T2, okay? Okay. So, and I'm asking that, what is the conditional probability? In other words, what is the probability of X will be greater than T1 plus T2, given that X is greater than T1. So that is the conditional probability. Remember that the conditional probability, like P A given B, equal to probability of A intersect B divided by conditioning event, which is probability of P. In our case, this is A and this is B, right? So what is the intersection of these two events? So we know that X is greater than T1, and the second event, the X is greater than T1 plus T2. If this happened, this is already happened, right? So in other words, these two events should occur at the same time. So that's mean the intersection or a condition that satisfies the intersection of these two events is simply the first event, right? The probability of X greater than T1 plus T2. Why? Because this happened, that will be already happened. Okay, the happening of this event will satisfy the happening of this event. That's why again this corresponds to A intersect B, and this corresponds to B. And instead of, so for the A intersect B, I can directly write probability of X greater than T1 plus T2. Okay, just remember that that is T1, that is T2. If this part happened, that means this is already happened. Okay. Well, you can think that like, let me change the color. You can think that this is an event, and that is another event. You can think that the intersection of these two events is this one, but that's not correct, right? Because the intersection mean that there should be some common points between those events. So what I mean in this example, if this happened, I cannot satisfy this event. That's why I'm not taking this one. I'm taking that one, okay? So simply, if that happened, the X greater than T1 plus T2, that means that events have already happened. Or the happening of this one, the occurrence of these events, will satisfy the occurrence of these events. That's why I can just take the probability of X greater than T1 plus T2, okay? So remember that the CDF, actually the CDF of any variable, any distribution, meaning that probability of X will be less than or equal to some value, right? But here I have X greater than something. That's why I can rewrite this part as 1 minus probability of X less than or equal to T1 plus T2. And also I can write this part as 1 minus the probability of X is less than or equal to T1. What is this? This is actually the CDF, okay? And what was the CDF of exponential function? That is fx x equal to e e to the minus, sorry, 1 minus e to the minus lambda x. Okay. So, and this is, instead of this one, I can write this one, and that will be 1 minus e to the minus lambda x, and this will be 1 minus 1 plus e to the minus lambda x. These two guys will cancel each other, and I will end up with e to the minus lambda x. E to the minus lambda x, and for the numerator, my x is t1 plus t2. So that will be e to the minus lambda times t1 plus t2 divided by e to the minus e to the minus lambda t1. So for the denominator, my x is t1. There's e to the minus lambda t1s will cancel each other such that, let me write it all clearly, e to the minus lambda t1 times e to the minus lambda t2. So I just opened this one, this power, which is t2, and divided by e to the minus lambda t1. These two guys will cancel each other, and I will end up with e to the minus lambda t2. Okay. So here, there is something important in this example. Let me clear the page. And let me draw the interval again to make it more clear. Let's say that is my interval, and it can go until infinity, and we will start from 0. So this point, this part is t1. Okay, this one is t2, and this one, this part, from this point to infinity, let's say that is t3. So the probability of t1 plus t2 plus t3 is, or let me write, the probability of t1 plus probability of t2 plus probability of t3 is equal to 1, right? So what I am asked that what is the probability that the x, the random variables, will be greater than t1 plus t2. So I am asked the probability of x will take the values in this region, in the region of t3. So let's associate that random variables with the transmission failure as we did in the first example. We start at the time of 0, and we don't have any failure until this point. And in other words, I'm asked to, I will not have any problem until that one. Okay? Because I'm asking to probability of having failure after this point. This information is given to me, and instead of calculating this one, I use 1 minus probability of T3, right? Actually. And this is 1 minus CDF of T1 plus T2, right? Probability of T1 plus T2, because that corresponds to probability of x will be less than or equal to some values. So that's the limit, and the probability of T1, 1 minus probability of T3 will give me this region, right? And actually what I calculate that way. So when I calculate this one, this whole region, I will end up the probability of this part. What that means, this part, the probability of all this part didn't affect from the previous one, the past, okay? So this given information didn't affect the probability of the feature. And that is called the memoryless property of the exponential function. Okay, that's why if I am asked something like that, and you will see in the next example, you can simply calculate the probability of this part, the remaining part actually. So T1 plus T2 minus T1, this part. So the probability of remaining part will be equal to this conditional probability. Okay. So let's look at another example, and let an exponential random variable with rate lambda denote the time for an event to occur, and let's call this random variable x. What is the distribution of the remaining time for the event to occur, given that event didn't occur before time t equal to t1? So let's say we have an interval that is t1, this part. We know that the event didn't occur at this time, okay? And in somewhere here, this event will occur, right? Like something here. And I'm asked to this region, the distribution of this region. Okay, this is actually what this question tells us. So again, let me draw the interval T1 and T2. So if we have an interval, and if we know the distribution of that that interval, or if we know if that variable, the first variable is, let's say, the exponential variable, the another part will be also the exponential, okay? Let's define the random variable y, denote this conditional remaining time from the solution of the previous question. We know that the probability y is greater than t2, given that x is greater than t1. Okay, so it is same with this example. So we know that this is e to the minus lambda t2. We just calculated it here. Okay. Then let's calculate the CDF of that new random variable, which is defined by y. So that will be the CDF of y, but within that condition, okay? And we will calculate the CDF for the point T2 for this one. So what I mean, actually, I'm going to calculate the probability of all this region. So what I'm calculating, the probability of y, y is less than or equal to T2. And I'm giving that the x, another random variable, greater than T1. And I know that that x is exponential random variable. Well, this is, I know that the probability of y is greater than T2, this one. When this information is given, the x is greater than T1, is this one, right? E to the minus lambda T2, okay? This part is e to the minus lambda T2. And this whole probability should be 1. And I can say that the remaining part is 1 minus e to the lambda T2, right? So, and this conditioning event, the past, will not affect the future, right? Will not affect the future. So I can simply write the probability of y is less than or equal to t2, this part is simply equal to 1 minus e to the minus lambda t2. What is this one? So this is the CDF of the exponential distribution, right? Then I can say that y is exponentially distributed with the same parameter lambda. Okay, this can be a little bit confusing, but don't worry, just remember that. Remember that the exponential distribution, exponential distribution has memory loss property. Okay, that is important. That means the past will not affect the future. Okay, if I ask you what is the probability of x greater than 100, given that x is greater than 30, pause the video and think about this question. We know that this part, the conditioning event, has no effect for the total probability, right? So does that mean can I ignore this part and can directly write which is equal to probability of x greater than 100? So because that has no effect. No, that is not true. Okay, this is actually equal to probability of x greater than 70, the remaining. But how? Let's say this is our interval, okay? And this is the first part, T1, and this is the second part, T2, and this is the last part, T3. What I'm asked, that this point is 30, and this point is 100. What I'm asked that the probability of x will be greater, the probability of x greater than 100. So I'm asking the probability of this region, right? Let me change the color. This region. This whole region. So the probability of T3, that region, actually is equal to the probability of 1 minus probability of T1 plus T2, right? Because I know that the probability of all events is 1. We just proved that. So if I calculate this one, that means I can find the probability of region 3, right? T3. So how can I calculate this probability? I can simply use the CDF, right? Because the CDF tell us the probability of x will be less than or equal to some value. So what I need to calculate at this point, I need to calculate the probability of this region, and this region means the x is less than or equal to 100, okay? And when I found that probability, if I subtract it from 1, I will find the T3. Remember the CDF of exponential function, which is exponential distribution, which is 1 minus e to the minus lambda x, okay? And we write that the product of T3 is equal to 1 minus e to the lambda T1 plus T2. And we solved this one in the previous examples. The result is e to the minus lambda T2, right? What is this one? Actually, this is the probability of this region, right? This region, T2, right? So that doesn't, so that's mean I'm calculating the probability of this region, and this region is actually the probability of the remaining part, right? Which is 100 minus 30. That's why this conditional probability is equal to probability of x will be greater than 70. Okay. And that is because of the memoryless property of the exponential distribution. In other words, in a more simpler way, if you are asked something like that, okay, there are three regions, let's say T1, T2, you can think every single point as a new experiment. So simply you can ignore this part and you can think that we start from the beginning, okay? You can think that point is a first beginning point of those experiments. That's why I'm calculating the remaining part. Because now, if I think this point as a new starting point instead of this one, this 100, this example, will be 70, and my 30 will be 0. What I'm asking the probability of this one, and this one is x is greater than 70. Okay, that's why I cannot directly ignore this one, but I can use that condition event to determine the new starting point of my experiment. Okay, so hope that is more clear now, and that is the end of part 2. Thanks for watching.